Welcome back to ECE 501B, one class period before exam number 2. Homework number 7 is due today, and I think that's as late as 11:59 p.m. If the Dropbox is still awake at that time, you can submit it by then. Exam number 2 review will be held in this classroom. We were allowed to do that. They said you may not be able to use the audio-visual equipment. Hopefully we'll be allowed to use the audio-visual equipment. But that's happening then, I don't know if it's 5:30, maybe 5:25, about 10 minutes after this class is the plan. I sort of get locked into even increments. But today what I want to do is quickly, for those that aren't able to stick around, I'll give you a little bit of the process for exam number 2. It should be consistent with the process that was followed for exam 1. Then we will actually jump ahead in terms of material. We won't be covering chapter 7 on this exam. It will be on the final. But everything is cumulative, so learning this is not a bad thing for what you'll be expected to know on Wednesday. But in chapter 7, which is dealing with now operators on inner product spaces, you need to be experts on inner product spaces for the exam. Now we're playing with operators on that. We'll quickly show why T dagger T minus T T dagger, that sounds better than the adjoint of T times T. But all of that combination is self-adjoint. We stated that after we described or verified that when T was normal, or T is normal, if and only if these norms are preserved when we operate on all vectors V in our vector space V by either the linear map T, or its adjoint. Those norms are equal. If those norms are equal, then your linear operator T is normal, and vice versa. If you have a normal operator, then you can use that result, and we will use that result to prove or verify some of these other steps later. Then there's quite a few things that result from having an operator that is normal, and we'll say those are the properties of having a normal T. Not that T can be abnormal, but we know what the definition of a normal operator is. A normal operator means that the operator and its adjoint commute. So whenever you hear normal, that's maybe one image you can think of. The other one would be these norms are preserved when the linear map or its adjoint are applied to a vector. If we do have a normal linear map T, then there are particular relationships between the eigenvalues and the eigenvectors, and that's corollary 7.7. So if T is normal, then we have this particular relationship. Really, they share the same eigenvectors. Their eigenvalues are conjugates of each other. If you now have a normal T and you have distinct eigenvalues, 1, 2, 3, 4, then the eigenvectors associated with those eigenvalues are orthogonal, and that's a nice thing. Whenever you can find orthogonal eigenvectors, that creates a lot of nice properties. That then leads us into the spectral theorems, and it really is easier to talk about these in two contexts. One, if you're playing in a complex inner product space, and the other is when your inner product space is real, or the field of numbers that you're living with is real. For the spectral theorem on the complex inner product space, you have this if and only if result. You obtain orthonormal basis if and only if T is normal. On the real, if T is self-adjoint, if T is equal to T star, or T is equal to T dagger, then you also have orthonormal basis. And those are some spectral theorems that are nice, and that allows us then to say a little bit more about these maps and their properties. If you have orthonormal basis, then things are nice. You can diagonalize these maps. And once you can diagonalize a map, you know a lot of properties. And this is now chapter 5. If you have a diagonal matrix, what do you know about those things on the diagonal? They're the eigenvalues. You also know that if all of those things on the diagonal, those eigenvalues, are non-zero, your map is invertible. Something else you can sort of just see once you have this diagonal matrix. And that even carries over when things are upper triangular. And we know that if you're on a complex vector space, all of these maps can be made to be upper triangular with the appropriate basis. All right, exam 2. So we're sort of jumping back and forth, but here's the process. Now we're getting into the lecture portion of those were the prelude to what we're going to do now. Exam number 2. We had 2 sheets of notes, I believe, because we had so many chapters before. But now we only have 2 chapters. So I'll just add 1 more sheet. If you want to make 3 new sheets, that's fine. If you want to just append to your original 2, the material is cumulative, meaning you may need to have access to some of that other material conceptually. We'll focus on problems dealing with chapters 5 and 6 and the homework problems on 5, 6, and 7. Today's homework is fair game for the exam. Any questions on the process? So you have 3 sheets of notes, basically 6 pages, but 3 unique pieces of paper. Is that okay? And if you can write on that edge, I guess you can put whatever you want on the edge, but I'm really concentrating more on the front and the back of your papers. I won't be examining the edge of your paper if you want to think 3-dimensionally with your sheets of notes. But we'll probably just stick with the plane, I would assume. All right. Now, that was chapter 5 and 6. We've now graduated into chapter 7. And proposition 7.6, just as a review, said that if we have a normal operator, then that's an if and only if relationship or statement with these norms. The norm of TV is equal to the norm of T dagger V for all V in this inner product space, capital V. That's proposition 7.6, and I believe we proved that last time at the end of lecture. So I'm not going to redo that. I just want you to keep that in mind, and that's sort of what you need to do for the exam on Wednesday, is have all of these things sort of right there in the frontal lobe so that if I'm asking something, you can sort of say, oh, by this proposition or by this theorem, I know how to relate what he's asking to what I need to find or what needs to be determined. During the process of proving proposition 7.6, I think we ended the day on saying, oh, T dagger T minus T dagger as an operator is self-adjoint. And I said, that's your homework assignment. How many went home and proved that to themselves? Good thing I'm not being recorded visually, huh? I would just have this look of being upset. Did I expect that answer? Maybe. But am I disappointed? Yes. All right, let's move on. So here's the proof. What do I need to do? I need to show that if I take the adjoint of that combination of maps, that I end up with what's inside the parenthesis that I'm taking the adjoint of. And we just have to remember how to play with products and adjoints is really the big deal here. But if we take the adjoint of a sum of terms, that's equal to the adjoint, the sum of the adjoints. That's the first line. The next line is to take the adjoint of things in the parenthesis. And it's like this matrix multiplication. If you took the inverse of AB, what's that equal to? B inverse A inverse. You can reverse the order. Well, you do the same thing when you're taking the adjoint, meaning if we look at this first term on the first line on the right-hand side of the equality, now we're looking at T dagger T daggered. So the first thing we need to do is put T down with a dagger. Then we follow that with the dagger of T dagger. If that makes sense. Over here, then we subtract T dagger dagger times T dagger. Is that what we had? Yes. And now we simply remember that the adjoint of an adjoint, we're back to the original map. And we end up then with T dagger times the original map T, and that's what we were hoping to get for our first term, minus T times T dagger. And so yes, that map, or that combination, creating a new map is self-adjoint. Questions on that? Yes. So I haven't said anything about, oh, did I didn't even need to have T being normal, did I, in this? Now, this fell out when we were doing T being normal in the proposition of 7.6, but I believe this particular result is independent. If you look at all of those steps, I haven't had to commute T with T dagger, have I? So I haven't had to worry about T being normal. So this result holds for a linear map T and its adjoint in general. So now if T is normal, then T commutes with T dagger, and we could commute either of these terms, and then we do have 0. Other questions? How much more do I have already pre-written? This is kind of easy. Maybe I should just do this all the time. No. There's, I think, some added benefit for you writing down as I write down, but this is where we're headed. Properties of T being normal. Now we do want to focus on T being a normal operator. And we'll look at two different scenarios, basically two different corollaries. The first one is, what's the relationship between the eigenvalues and the eigenvectors when T is a normal operator? So, and we've already stated what that relationship is, but we want to see that or prove that. And then, if we do have a normal operator T, and if T has distinct eigenvalues, then the eigenvectors associated with those distinct eigenvalues will be orthogonal eigenvectors. We're not saying that all of the eigenvalues of T are distinct, but of the distinct eigenvalues, they will have corresponding eigenvectors. Those eigenvectors are orthogonal. I'm just sort of writing it very quickly here. We'll state it more thoroughly in the corollaries. That's where we want to go. So let's look at the first one, which is dealing with the eigenvalues and the eigenvectors when T is a normal map. And that's actually corollary 7.7. In corollary 7.7, it says, given T, a linear operator on a vector space V that's normal. Now if we take a vector V that's actually an eigenvector, so now if V in that vector space is an eigenvector. Of that linear map T, and it's actually an operator, isn't it? Since it has eigenvalues and eigenvectors, these have to be square operators. It's only dealing with this vector space V mapping back into itself. With respect to that eigenvector V, we also have an eigenvalue, we'll call it lambda. So we have an eigenvalue-eigenvector pair for the operator T. Then V is also an eigenvector of the adjoint map, T dagger, with an eigenvalue being the complex conjugate. So T and T dagger share eigenvectors, and their eigenvalues are conjugates of each other. Let's look at the proof of that corollary. And to start, let's just take what we've already defined or identified in this corollary. Take V and lambda as an eigenvector and eigenvalue of T. If that's true, then we know that V lives in the null space of some map. And this is chapter 5. But the map is now T minus lambda I, V is equal to 0. We know that's true if lambda and V are eigenvalue and eigenvector for the linear map T. Now, what I'm going to do is actually show that if T is normal, so is T minus lambda I. And since that's kind of its own little result, I'm going to call that a lemma and just prove that inside the proof of the theory. So here, let me just say that I now have a lemma. It's a minor result that sort of gets us partway to our end goal. If T is normal, and that's given in the first statement of our corollary anyway, so we're just being consistent with our corollary. If T is normal, then T minus lambda I is normal. So this lemma is sort of an aside little piece that will help us. Now, if I want to show that something is normal, what's one way of doing that? Can I show something? If I could show that T minus lambda I times T minus lambda I adjoint was equal to its reversed product, T minus lambda I adjoint times T minus lambda I, then I would show that T minus lambda I is normal. Another way of saying that is that this operator, T minus lambda I, commutes with its adjoint. Let's look at both sides and just see that we end up with the same result. So let's start with the left-hand side of that equality. And that's now t minus lambda I times t minus lambda I adjoint, which is one of the reasons why I went through that earlier result of adjoining some operators. The adjoint of that t minus lambda I sum is now the adjoint of t. And what happens if I take the adjoint of lambda I? What's the adjoint do for us? If we have orthonormal basis, it's just the complex conjugate transpose of the original map. And I, we can transpose that as much as we want, and we can take the complex conjugate, we still get I back. The only thing that really happens is that we now have the conjugate. Ooh, that's an ugly conjugate. That's not much better, but the only thing that I've really buried here is that, or used, is that the adjoint of I is equal to I. Are we okay with that? So that I've used. Now let's just keep going. Let's form that product. I have t times t adjoint. Then I have minus lambda I times t adjoint. Then I have minus t lambda star I plus lambda lambda star I times I, which is just I. And lambda star are scalars. I can slide those back and forth. I then have t dagger minus lambda. And I times t dagger is just t dagger. And if I pull that lambda star to the left and multiply t times I end up with t. And then lambda star is just the absolute value of that eigenvalue squared. That's the left-hand side. Let's now look at the right-hand side and see if we don't get the same result. If it does, then we've proved that limit. We've shown that that t minus lambda I is normal. The right-hand side was t minus lambda I adjoint times t minus lambda I. We can take the adjoint of that first term, which is t dagger minus lambda star I times t minus lambda I. Then we have t dagger times t minus lambda star I times t minus t dagger lambda I plus lambda star lambda I squared, which is I. But if t is normal, which is the very first assumption, then we can commute those products that's in the first term. I now have t times t dagger. I have minus lambda star t minus lambda t dagger plus lambda absolute value squared times I. And now the only thing I have to realize is that maybe I need to shift those middle terms one for the other, but now the right-hand side and the left-hand side are equal. I hope that you now believe that that finishes up the proof of that lemma that t minus lambda I is normal, because it commutes with its adjoint. Now we can continue on with our proof. Since t minus lambda I is normal, then via prop 7.6, and that was the very first thing we talked about in our introduction to today's class, that was this normal operator is norm preserving when we have that and its adjoint inside this norm. Meaning, we can now say that the norm of t minus lambda I v, that's equal to the norm of t minus lambda I adjoint v. That's by proposition 7.6. Is that okay? But now that we need to leave well enough alone, didn't think it was well enough. Now what happens? Now I have, as an operator, I have t dagger minus lambda star I times v. But what do I know about t minus lambda I v in terms of its norm? Lambda and v, I assumed in the first, were eigenvalue and eigenvector. T minus lambda I v is 0. So its norm is 0. That means that all these terms are 0. But now I can say, oh, that means that t dagger minus lambda star I v is equal to 0. And that's then another eigenvalue-eigenvector relationship. That says that v is an eigenvector of t dagger minus lambda star I. Whoops, what am I doing? Going to sleep. V is an eigenvector of t dagger, by definition of an eigenvector, with the eigenvalue equaling the complex conjugate of the original operator's eigenvalue. So now we've shown the relationship between eigenvalues and eigenvectors when t is normal. We said we had another corollary that we wanted to look at when we had normal operators, and that's corollary 7.8. Given a normal operator, so given t, that's a linear operator on a vector space V, and that operator is normal, so we know t dagger is equal to t dagger t. Then with respect to that operator, the eigenvectors of t corresponding to distinct eigenvalues are in fact orthogonal. So if we have distinct eigenvalues in this operator, then the eigenvectors associated with those distinct eigenvalues are orthogonal. And that's kind of a nice result. Let's now prove that by first taking alpha and beta as distinct eigenvalues. and we'll go ahead and just assume eigenvectors u and v for each of those respectively. What we have then is we have tu is equal to alpha u, and we have tv is equal to beta v. Now let's create a particular relationship that we can expand on. Suppose I now look at a scalar, alpha minus beta, times the inner product of u and v. I can distribute that scalar across that, or with that inner product, and I can now say I have alpha uv minus beta inner product of u and v. And now by the homogeneity in the first slot, that's now alpha uv minus, and now let me put that beta in the second slot. If I do that, what happens? This is review for exam 2. It's beta star, isn't it? It's the complex conjugate of beta. We now have beta star v. But what is alpha u? That's tu, inner product with v. And beta star v and what did we say t was? T was normal. So now if we have the conjugate of an eigenvalue, now we know that that's the adjoint operating on that vector v. But now what do we know about that last line? tuv minus u t dagger v. So I could make this tu comma v. This is the definition of an adjoint, isn't it? So this now, those two terms, those inner products, those scalars are equal. I could rewrite that, but if we just realize that that's the definition of the adjoint, that gives us 0. That's x minus x, essentially. This is now equal to 0. By the definition of the adjoint. But now, if we have all of that equal to 0, let's go back to what we started with, and now we have that alpha minus beta times the inner product of u with v is 0. But alpha and beta, remember, we said were distinct, which now says that alpha minus beta is non-zero. So we'll be able to divide that out, and that's what we want. Now we know that alpha minus beta, scaling the inner product of u with v, is equal to 0. And since alpha and beta are distinct in our assumptions, then alpha minus beta is non-zero. So we can divide that non-zero number out and get uv equal to 0. So what? What's that tell us? Now we know that those two vectors inside that, yes, we need to call a timeout. No. there's another way of thinking of this, isn't it? Besides a timeout, this doesn't make much sense, I guess, if you're just hearing this orally. But they're orthogonal, aren't they? These two vectors, u and v, that's the definition of orthogonality. So this now says and that's actually what we set out to prove, wasn't it? We wanted to prove that the eigenvectors associated with distinct eigenvalues actually result in those eigenvectors being orthogonal. But that result depends on t being normal. That was the first condition in that corollary. But now we have those results associated with operators being normal. Let's now look at the next result, which was sort of the end result that we were hoping for, and that is this spectral theorem. And this is actually allowing us to do quite a bit. So we now come let's say to the end of our journey or our quest to find nice basis for these operators. And nice probably means, can we find a basis where we can diagonalize these operators? And that's the spectrum. Our spectrum will live on these on the diagonal. So really remember the appeal of diagonal matrix representations. There's a lot of nice things about that. Now we can immediately think of these orthonormal basis vectors, and we're just scaling and either contracting or expanding along those vectors with this diagonal representation. Also, remember that an operator only has a diagonal representation if there exists a basis consisting of eigenvectors of the operator. So now we like to have this basis being eigenvectors, and let's go ahead, now that we've introduced inner product spaces that allows us to determine when vectors are orthogonal to each other or orthonormal, we can compare, or we can scale those vectors to be orthonormal. We'll add that. We'll add further constraint that we'd like an orthonormal basis. And that was one of the reasons why we spent time in chapter 6. Orthonormal means that we need to have an inner product space. That gives us this length and orthogonality. So we must be in an inner product space. And this spectral theorem actually tells us which operators have eigenvectors that can produce such an orthonormal basis, and therefore which operators have a nice diagonal representation. And what kind of properties we need these operators to have depends on whether we're dealing with a complex inner product space or a real inner product space. So we'll look at those two separately. So let me just say that the answer relative to this spectral theorem, the answer depends on whether we're dealing with a real or complex inner product space. So we'll look at those two different cases. One where we're living on a complex inner product space, and another when we're dealing with a real inner product space. And the complex inner product space is actually a little cleaner, so let's look at that one first. So here is the complex spectral theorem. And that's number 7.9 in the textbook. Now our inner product space is a complex inner product space. So V is a complex inner product space. And T is a linear operator on that space. This complex inner product space V has an orthonormal basis consisting of eigenvectors of the linear operator T if and only if T is normal. So if T is normal in a complex inner product space, then we can diagonalize that operator. T now needs to commute with its adjoint. And if it does, then we know we can diagonalize that mapping. Or if T V's norm is equal to T dagger V's norm, then T is normal, and again, we can diagonalize that linear map. Since this is an if and only if proof, or I should say theorem, how do we prove it? We have to go both ways, don't we? We have to go forward or use one set. Let's say assume we have an orthonormal basis, show that T is normal, and vice versa. Assume T is normal and then show that we end up with an orthonormal basis. So if we had this double-headed arrow, we need to make sure that arrow is going in both directions, or it implies both ways. First, let's assume that V has an orthonormal basis of eigenvectors. And since we are saying that, that immediately is telling us that we're playing with an inner product space. So now we're assuming V has an orthonormal basis of eigenvectors of T. That's the assumption. We now have to show that T ends up being normal for this first direction. But what do we know about any operator T on a complex inner product space? Well, maybe I'm getting ahead of myself. If we know that T has, or V has an orthonormal basis of eigenvectors, what do we know about T? If we have orthonormal eigenvectors, then if we put this in that basis, then the matrix representation of T is going to be diagonal. So T then has a diagonal matrix representation with respect to that basis. Now, what do we know about the matrix representation of the adjoint of T? It's the complex conjugate transpose of T, isn't it, in this basis? This basis is orthonormal, and when we have that, then we know that the adjoint is just the complex conjugate transpose of the operator. So the matrix representation of the adjoint of T is the conjugate transpose of the matrix representation of T. Which says then in general, then we can say that the adjoint, therefore the adjoint also, if T was diagonal in terms of its matrix representation, we do the complex conjugate transpose, it's also diagonal. So T dagger, or the adjoint of T as a map, also has a diagonal form with respect to this basis. What were we trying to do? We were trying to show that this particular map is normal. So for something to be normal, we need t times its adjoint to equal its adjoint times t. So now that we have these diagonal maps, let's just consider the product of diagonal maps, and I hope you can see what we've got. Consider the product of two diagonal matrices. In this case, we could just say A1, A2 down to A sub n, B1, B2 down to B sub n. They're the same size. And what's the result? A1 just scales B1, A2 scales B2. We really just have this product of A's and B's on the diagonal. And I hope that it's clear that we get the same result when we reverse those and have B times A. Get the same result from B1, B2, Bn times A1, A2, An, which is B1, A1, but those scalars commute. So now that we have, therefore, any two diagonal matrices commute, which says that T dagger is equal to T dagger T, which says then that we have reached the end that we wanted, and that was to show if we started with this set of orthonormal eigenvectors, we could show that the operator T was indeed normal, and now we've shown that. So we've gone one direction. Now if we go in the other direction, what's our assumption? Now we start with the end and go back the way we tried to get to the beginning. So now we're going to assume T is normal. Now for any map T, we can say based on chapter 6, chapter 5 material, that now for any map T in a complex inner product space, which is what we are living on in this part, this is the complex spectral theory, given any map T, we can get an upper triangular representation, matrix representation of that map T. So far we haven't used the fact that T is normal, but we're assuming T is normal. But we can now say that T has an upper triangular representation. And that's true for any operator on a complex vector space. Since that's resulting from a chapter 5 result, which is before chapter 6, which was before we started talking about inner product. So the fact that T has an upper triangular representation hasn't yet needed any of this inner product stuff. But now that we have an upper triangular matrix, let's say T on some basis, E1 through E sub n, what does that look like as a matrix? That's just this A11, A22, A33, ANN. We have a 0 down here, but over here we have A12, A1n, and all of these other terms. But we know that that basis is orthonormal. If we had just a set of vectors, we could orthonormalize that because now we're on a complex inner product space, and Graham-Schmidt allows us to find these orthonormal vectors, E1 through E sub n. So if we have this relationship, or in this representation of the operator, then in order for this matrix representation to be invariant with respect to E1, then we actually are going to have this A11, A22, A sub nn, A sub 1n, we need to just have a non-zero upper element in A11. So now really what we're wanting is this norm of that, or we will use the norm of this in a minute. But what we're really saying is that E1 is an eigenvector, and it's invariant with respect to t. And if that's the case, then we need to stay in that same direction when we operate on that matrix with that vector. And that vector, let's say E1 is now 1, 0, 0, 0. Now we have to stay in that direction, and we do when this is an upper triangular matrix. You're just pulling off that first column. Now, if I ask for the norm of TE1 squared, what's that going to be? That's just A11 squared, isn't it? Especially if you just looked at this as a vector and said, what's the norm of that squared? You could just say, give me the inner product, the Euclidean inner product of this vector with itself. And that's going to just take the first term and square it, its magnitude. Now, what happens if we looked at the matrix representation of the adjoint of T? The matrix representation of the adjoint is the complex conjugate transpose of T, and we said the matrix representation of T was this upper triangular matrix. Now if we do the complex conjugate transpose, this first row becomes the first column, and all these other rows become columns below the diagonal. So now, we can consider the matrix representation of the adjoint of T as the conjugate transpose of the matrix representation of T. And now what if I wanted to find the norm of that squared? Now I have all of these these scalars in the first column that are weighting really orthonormal vectors. And that goes back to that norm squared is equal to just the weightings absolute value squared to get the norm squared. And we know what those weightings are. Those were just in the first row of our matrix representation of T. So now we know that this is A11 squared plus A12 magnitude squared all the way down to A1n magnitude squared. Now we need to go back to our original assumption in this half of the proof, which was to say assume T is normal. If T is normal, then we know that this value better be the same as that value if our operator T is normal. If that's the case, so let me write down what I'm now using, but T is normal by assumption, and from proposition 7.6, I told you we would use that. That was the first one of these statements that we were recalling from the last lecture. From proposition 7.6, we know that TV squared is equal to T dagger V squared, or norm squared. And we can now just take V to be E1, because that's true for any vector. Then we see that this implies that the norm squared of TV, which was just A11 squared, is supposed to equal the absolute value of A11 squared plus the absolute value of A12 squared, all the way down to the absolute value of A1n squared. If the left side is equal to the right side, all of those trailing A's need to be 0, because we only have the first two pieces. A11 magnitude squared is equal to A11 magnitude squared. Meaning we can conclude then that A12, A13, all of those terms in the top row of that matrix representation of that linear map T must be 0. If we now incorporate that fact into the matrix representation of T, now we know that that upper triangular matrix has a little bit more structure to it. Now the top row is all 0 except the first entry. Now, do you see that we can actually iterate on this process? Now we can look at TE2 and equate that, and now these second row entries off the diagonal are going to become forced to be 0. But we can repeat this process for all of these other E sub n's. Meaning with E sub 2, we would actually find that this A sub 2 magnitude squared was A sub 2 magnitude squared plus A sub 3 squared down to A sub 2n squared, which forces all of those remaining terms to be 0. And that's true in all of the rows. Of this matrix representation of T. So we're actually forcing the issue. So we're forced to conclude that the off-diagonal elements are 0. And so the matrix representation of that linear map T is a diagonal matrix. Which now says that the eigenvectors of T are in fact or do form an orthonormal set of vectors. So there's our complex spectral theorem. What did that say? That said if we had an operator T that was normal, we can essentially diagonalize the matrix, or diagonalize the matrix representation of that linear map. Now what we want to do is see how far we can go if we have a real inner product space. But before we do that, we need some preliminary results. So that's going to take us through some more lemmas. So before tackling the case for real inner product spaces, we need some lemmas. So let's now look at lemma 711. So now we all need a little 7-Eleven at this point, maybe to get some caffeine, right? So this lemma is going to help us out. So now we have this lemma 7-Eleven, not lemma quick trip. Have to be fair in advertising, right? So now this is lemma 7-Eleven. Suppose we have a linear operator T on a real on a vector space V. And suppose that that operator is self-adjoint. Now assume that we have two numbers, alpha and beta, that are real, such that alpha squared is actually less than 4 beta. Then we can actually create another map that's t squared plus alpha t plus beta I, and we can actually say something about that map. As long as alpha squared is less than 4 beta, then this map made up of t squared plus alpha t plus beta I, with t being self-adjoint, that map is invertible. That's our lemma. That's lemma 711. So let's see if we can prove that. And again, we're going to be dealing with real inner product spaces, and we've shown, I think, and if we haven't, you need to be comfortable with that for the exam, that you might end up with a matrix that doesn't have any eigenvalues in a real inner product space or in a real vector space. Chapter 5, I guess we don't, yeah, we just needed a real vector space. Here we go. So let's now assume that alpha and beta are real and that they satisfy that last relationship, that alpha squared is less than 4 beta. And let's let V be a non-zero vector in this vector space V. Now let's look at the inner product of t squared plus alpha t plus beta I V with V. If we look at the linearity of the first slot, then we can push those three pieces into three different inner products. We have t squared V V plus, and we can pull out the alpha and the beta from the first slot. We have alpha TV V plus beta V V. That's the linearity of the first slot. Allowed that result. Now let's use the definition of the adjoint to split that t squared, meaning t squared is t times t. And if I now have t times tv, I can push that t over to the second slot in the form of an adjoint, so that I now have tv t adjoint v plus alpha tvv plus beta v v. And this is just the definition of the adjoint. Now, did I say anything about t? I said t was self-adjoint, didn't I? So now what do I know about that t adjoint in the first inner product term? It's just equal to t, isn't it? So now I have tv inner product with tv plus alpha tvv plus beta vv. But now I can clean that up a little bit because I have vectors inner product with themselves. So those are now norm squared. I now have the norm of TV squared. So this was the self-adjoint property. Plus, and let me pull that other term over, that's just V squared, scaled by beta, plus alpha, inner product of TV with V. And that's just these norms. Now I want to use a result that you may have to use on the exam. And then we'll probably have to stop at that point. But now what I want to say is I want to actually find a lower bound on this expression. And if I use the Cauchy-Schwarz to lower bound this, we know the absolute value of the inner product is less than or equal to the norm of the two vectors in that inner product. So that now to lower bound this is bigger than the negative of the norm of TV times the norm of V scaled by alpha, by the Cauchy-Schwarz. So now I can actually say that this is greater than or equal to the norm of TV beta times the norm of V squared minus alpha times the norm of TV times the norm of V. And this and we'll finish this up after the exam, but now I'm going to complete the square because I want this to be bigger than 0. If I can force this to be bigger than 0, then I know that that quantity, or the vector v, is not in the null space. Uh-oh, now I'm going to slide it before the picture. But now I know that this v is not in the null space of that matrix. And if I don't have a null space, if the null space is trivial, then it's an injective map. If it's injective, I now have an invertible map. And that's what I wanted to show. So that's what we'll finish up with next time. Thank you for tolerating going over. And I'll see you for the exam.